The universe. For millennia, as we have gazed upon the starry sky, a profound question has echoed in our minds. Just how vast is the universe? And what lies beyond its cosmic horizons? Humanity may not uncover the answers for hundreds or even thousands of years, perhaps never. However, using the small discoveries we have made, we can still analyze what might exist beyond our universe.
When we speak of the universe and its size, we often describe it as infinite. By definition, the universe is the union of all space and time. But if the concept of infinite space is difficult to grasp, let's consider the other component, time. Is time also infinite?
To us, time seems endless. According to our current understanding, time is an objective form of matter's existence, a continuous expression of its movement through past, present, and future. Whether time progresses linearly, spirally, or in some other manner we have yet to comprehend remains unclear. What is clear, however, is that time changes as matter changes. Matter is neither created from nothing nor destroyed into nothing. As an objective manifestation of matter and its continuous change, time itself must be linked to this principle. Through a series of observations and calculations, humanity has estimated the current age of the universe to be 13.8 billion years. If the universe has an age, it implies that time is finite. Since the universe is a combination of space and time, this suggests that the universe itself is finite, not infinite. An infinite universe could not be created within a finite amount of time. In our daily lives, we are familiar with the sound of a train. As it approaches, the pitch gets higher. As it moves away, the pitch gets lower. This is the Doppler effect, proposed by Austrian physicist Christian Doppler in 1842. It describes the change in wavelength of a wave in relation to an observer who is moving relative to the wave source. When the source moves toward the observer, the waves are compressed, their wavelength shortens, and their frequency increases. This is called a blue shift. Conversely, when the source moves away, the wavelength lengthens and the frequency decreases, known as a red shift, so named because red light has the longest wavelength in the visible spectrum. This principle allows us to calculate the speed of a wave source relative to an observer. The Doppler effect applies not only to sound waves, but to all types of waves, including electromagnetic waves. In 1912, American astronomer Vesto Slipher discovered that the frequency of light from stars also changes with distance. If a star is moving away from us, its light spectrum shifts toward the red end, a galactic redshift. If it's moving closer, it exhibits a blue shift. He observed that red shifts were far more common than blue shifts, suggesting that nearly all galaxies are moving away from us. In 1931, Edwin Hubble, after whom the Hubble Space Telescope is named, built on this discovery. He found that almost all galaxies exhibit a redshift, and a galaxy's recession speed is directly proportional to its distance from us. In other words, the farther away a galaxy is, the faster it is moving away. This is Hubble's law. The fact that galaxies are receding from us at an accelerating rate indicates that the universe is expanding. Hubble was not the first to propose this. The idea of an expanding universe came from Belgian astronomer Georges Lemaitre. Thus, the law is more accurately called the Hubble-Lemaitre law. More importantly, in 1931, Lemaitre further proposed that the universe is expanding because it originated from a single point, a primordial atom, which grew from a tiny seed into a colossal tree. This concept became what we now know as the Big Bang Theory. At the time, this was a radical idea that many astronomers dismissed as absurd. However, a series of crucial observations later provided strong evidence that our universe likely did originate from an explosion. The most significant piece of evidence is the cosmic microwave background, CMB, radiation. In 1965, two engineers at Bell Labs, Arno Penzias and Robert Wilson, detected a persistent background noise while working on a sensitive radio antenna for satellite communications. Even after cleaning bird droppings from the antenna, the noise remained. This noise was later identified as the thermal radiation left over from the Big Bang, a remnant from about 380,000 years after the initial explosion, when the universe's radius was roughly 40 million light-years. Over 13.8 billion years of accelerated expansion, the universe has grown to its current size. The discovery of the CMB cemented the Big Bang theory as the most widely accepted cosmological model. So, we have established several key characteristics of our universe. It originated from a singular point in an explosion, it is expanding at an accelerating rate, and the most distant parts are receding faster than the speed of light. But if the universe is expanding, why aren't our distances to the sun and moon increasing? This is because cosmic expansion does not affect the distances between gravitationally bound objects like the Earth and the sun. On the scale of our solar system, gravitational and electromagnetic forces act like an invisible rope holding everything together. Cosmic expansion is the expansion of space-time itself. It does not change the relative positions of objects within a bound system. Since our solar system orbits the supermassive black hole at the center of the Milky Way, the distances between stars within our galaxy also remain stable. However, beyond the Milky Way, with the exception of a few dwarf galaxies and gravitationally attracted neighbors, all other galaxies are moving away from us. Imagine the universe as a balloon being inflated. Galaxies are like dots on its surface. As the balloon expands, the distance between the dots increases. Given enough time, the space around the Milky Way will eventually become a vast, empty, dark void. Before we can determine what lies outside the universe, we must first determine its size. What we call the observable universe is a spherical region centered on the observer. We can see the farthest reaches of the universe because light from those distant places has reached our eyes. The most distant light we can currently observe comes from 13.8 billion light-years away. This might suggest the radius of the observable universe is 13.8 billion light-years. However, that is just a snapshot of the light's position 13.8 billion years ago. Due to the continuous expansion of the universe, the current position of that source is now much farther away. By applying Hubble's cosmic expansion constant, we calculate the actual radius of the observable universe to be about 46.5 billion light-years, making its diameter 93 billion light-years. Is this 93 billion light-year diameter the true size of the universe? No. The actual universe is likely much, much larger. Since the universe expanded from a single point and is still expanding, it must be finite, no matter how large. If it is finite, it must have a shape. According to the theory of relativity, space-time can be curved. Therefore, the universe might have a spherical structure. In A Brief History of Time, Stephen Hawking discusses Einstein's view of the universe as finite yet unbounded. Einstein believed that space, curved by the matter and energy within it, would eventually close in on itself to form a three-dimensional hypersphere. This suggests a spherical universe. Much like how we can walk forever on the surface of the Earth without ever reaching an edge, the universe could be similarly structured, albeit in a way that is different from a simple three-dimensional sphere. There is other evidence for a spherical universe. One classic observation is that the universe appears largely the same in all directions from our vantage point on Earth. This leads to a bold hypothesis. Could it be that one of the most distant galaxies we observe is actually our own Milky Way? The light may have circumnavigated the spherical universe, meaning the farthest thing we see is, in fact, ourselves. After all, we have never seen the true, complete shape of our own galaxy. The distribution of the CMB also suggests other possibilities. In 2003, a team of French astronomers proposed that the universe might have a more complex shape, such as a dodecahedron. In this strange topological structure, traveling out through one face would cause you to re-enter through the opposite face. Another theory, proposed by two former Soviet astronomers, suggests the universe has the connected structure of a torus, or a donut. This would also mean the universe is connected in some way, with galaxies moving apart on its expanding surface. There is also the possibility that the universe is flat. This doesn't mean it's a two-dimensional plane like a sheet of paper, but that its overall geometry does not curve light. A small black hole can bend light, so the immense mass and energy of the entire universe should also affect light's path. If the universe were a sphere, two parallel beams of light would eventually converge due to gravity. If it were a curved surface, like a saddle, they would diverge. However, for 38 billion years, light appears to have traveled in straight lines. This leads to the conclusion that the universe is flat. The only way this could be true is if there is a much larger universe beyond our observable one, and its curvature is so minuscule that it is currently undetectable with our instruments. The boundary of the observable universe is called the cosmic event horizon, the maximum range from which electromagnetic waves can reach Earth. Beyond this horizon, space is receding from us faster than the speed of light, so its light will never reach us. The space beyond this boundary can be thought of as a region that the Big Bang's expansion has not yet reached, a reserved space for the universe's final form. If the universe is like an inflating balloon, it might one day reach its limit and burst, causing everything to return to its origin. This outside could be understood as a dark space, analogous to dark matter and dark energy. We cannot observe them, but their effects suggest they must exist. We call them dark because we cannot see them or understand their properties. Perhaps this dark space contains nothing at all, no time and no space. Another possibility is that beyond our universe lies an unimaginably vast hyperspace containing countless other universes. This leads to the idea of a parallel universe. While many scientists are skeptical because it is unobservable and difficult to model with physics, the hypothesis is gaining acceptance as it can explain certain paradoxes of space-time. According to quantum theory, when an event occurs, it can have multiple outcomes, and each possible outcome creates its own universe. These universes would follow the same fundamental physical laws as ours and would contain countless versions of our world and of you. These parallel universes are also expanding and exist within this immense hyperspace like bubbles, some far apart, some close, and some even overlapping. Such an overlap could cause changes in our universe, like the Mandela effect, where memories of different outcomes from other parallel universes might influence our own. Of course, this is just speculation. The number of parallel universes could be vast, but likely still finite. Another possibility within this hyperspace is the existence of universes with completely different physical laws. According to the extraspatial dimensions of M-theory, there could be trillions of different shapes for these universes. Some might be like ours, capable of supporting life. Others might be completely lifeless, without even stars or galaxies, failed or undeveloped universes. This is the multiverse theory. It's like a laboratory experiment where you add culture medium to many petri dishes to grow microorganisms. Some might cultivate beneficial bacteria, while others grow nothing at all. Our Earth just happens to be in one of the successful dishes. This leads to an even bigger question. If this hyperspace exists, what lies beyond it? Before we explore that, let's look at the theory of cosmic inflation. Based on the CMB, we would expect the temperature of radiation from different celestial bodies to vary. For instance, matter ejected earlier in the explosion should be cooler than matter ejected later. But astonishingly, when scientists measured these radiation temperatures, they found them to be almost perfectly uniform, no matter which direction in the universe they looked. It's as if you measured the temperature at point A, 13.8 billion light-years to your left, and at point B, 13.8 billion light-years to your right, and found they were the same. This would only be possible if Earth were the epicenter of the Big Bang. To explain this, supporters of the Big Bang propose the theory of cosmic inflation. It suggests that immediately after the Big Bang, the universe did not expand right away. Instead, matter and energy mixed thoroughly in an extremely small space before undergoing a period of hyper-accelerated expansion. This ensured that all bodies in the universe would have a similar radiation temperature. After this burst of inflation, the expansion slowed down to its current rate. If we compare the universe's expansion to a missile, it didn't travel at a constant speed. It changed speeds at certain points as if to hit a specific target. This behavior seems unnatural, almost designed. It's like a bus driver who circles the city slowly until enough passengers are on board, then announces, "Everyone hold on, we're setting off now," and accelerates rapidly. After a while, feeling that a slower speed is sufficient to reach the destination on time, the driver slows down and arrives as scheduled. This is almost incomprehensible. Why would the universe behave in such a peculiar way? It feels less like a coincidence and more like a pre-designed outcome. Given the non-natural aspects of inflationary theory, it's possible that our universe, and even the hyperspace beyond it, exists within a higher dimension, or something that transcends even higher dimensions. Imagine we developed a game with an infinitely large map and gave the in-game characters a degree of intelligence, allowing them to develop freely. As the game progresses, these characters might also begin to wonder what lies beyond their seemingly endless world. Could they ever conceive of us, the players, observing them from in front of a computer screen? Perhaps. Our own universe, from the smallest to the largest scales, shows interconnectedness, just as the games we create are based on our real lives, only perhaps more exaggerated and fantastical. What if those game characters one day have the same thought, that they can perceive something beyond their universe?